So let's continue with section 6.3, and this is going to be exponential equations and inequalities. So the next section will do logarithmic equations and inequalities, but it's going to be really similar to this section in sort of in spirit. So the basic idea is going to be we're going to have some sort of inequality or equation with a logarithm or an exponential, and we'll have to use the other to suss it out. Your suggested exercises are 1, 7, 13, 19, 35, and 37. The key, this kind of looks like a 2, got a little weird tail there. The key concepts are going to be just solving equations and inequalities. The examples I'd like you to go through, so I'd like for you to work through, and these will be really helpful. Examples 1 and 2 in the book. The thing about these is that the basic technique that you're going to see here for most of the problems that we're going to see in this class is fairly straightforward, but the answers can look really ugly. So it's important to do enough examples that you don't get scared by the ugly numbers. I think I mentioned at the very start of class, I take great pains to make sure that the numbers aren't ugly, except in a few cases. This is one of those cases. So example, let's solve for x. We've got 7 to the 2x plus 3 equals 8 to the x minus 1. Now, before, so this would have been several pages ago, we were able to solve exponential equations when we had the same base, right? When I had 3 to a power, and this 27 is actually 3 cubed, so this was also 3 to a power. So 3 to 1 power equals 3 to another power. Well, those powers had to be equal. That's going to be a little bit more difficult to do here because 7 and 8 are certainly not exponents of the same natural number, right? It's, you know, if this was maybe 4,398 and 76,292, I don't know, maybe they're both powers of 6 or something. I don't think so. I mean, we could check that, but maybe there's something going on there. But here we really don't have a chance. So what we're going to do, we're going to write this equation again, and I'm going to leave a little bit of space. You'll see 7 to the 2x plus 3 equals, leave a little bit of space, 8 to the x minus 1. And what I'm going to do is I'm going to take the same logarithm on both sides. Okay, so just like if I had x squared equals 4 and took the square root on both sides, here I've got an exponential function on both sides, so I'm going to take the log on both sides. Now, you can take whatever base log you'd like, as long as you take the same base on both sides. I tend to choose natural logarithm for a very simple reason. If I were to do log base 5, I'd have to write 1, 2, 3, 4 symbols. If I were to take common log, I'd have to write 1, 2, 3 symbols. But if I write log, natural log, it's only 2 symbols. See, save time. Okay, whatever. Natural log is just a really nice, common thing to use. Anyways, when I'm here, now I can apply rule number 3, the power rule from the previous section, to pull those exponents out. So this, by rule number 3, the left-hand side is going to be the quantity 2x plus 3 times the number natural log of 7, and this is going to be the quantity x minus 1 times the number natural log of 8. Now I can distribute these in the following way, and I'm going to go a little bit more slowly maybe than necessary, just so you can see how this works. So this is 2x plus 3 times natural log of 7. Okay, that's interesting. Times the natural log of 7. So this is 2x times the natural log of 7 plus 3 times the natural log of 7. And this side is x minus 1 times the natural log of 8. So it's x times the natural log of 8 minus 1 times the natural log of 8. And that's just natural log of 8. Now I'm going to put all the x things on one side and all the non-x things on the other side. So I've got 2x times the natural log of 7 over here, and I'm going to subtract off x natural log of 8. And if you'd like, you can write natural log of 8 times x, but you just have to be careful that you set up parentheses like natural log of 8 times x, so that you know that you don't have natural log of 8x, right? We don't have this, we do have this. So you just have to be a little careful with how you write these expressions. On the right-hand side, we're going to subtract this from both sides. So we've got negative 3 natural log of 7 minus natural log of 8. But on the right-hand side here, I can factor out an x. Sorry, left-hand side. Left-hand side, I can factor out an x. So this becomes what? X times 2 times natural log of 7 minus the natural log of 8. Right-hand side stays the same. Negative 3 natural log 7 minus natural log of 8. And finally, I divide both sides by this quantity here. I get my final answer, which is x equals, let me give you a little bit more space here. This is going to take just a little bit more space to write. We get x equals negative 3 natural log of 7 minus natural log of 8 all over 2 natural log 7 minus natural log of 8. And this is the final answer. And like I said, this is a pretty ugly number. And you should normally, you know, if you're doing exercises in my class or if you're doing homework problems and exercises, they might end up being ugly. But if you're doing quiz problems or exam problems in my class and the numbers end up ugly, then there's probably an issue unless it's one of these. So these I get that these are kind of ugly, complicated expressions, but that's okay. So here, it's just tough to make these numbers work out nicely without making the questions fall back into the previous case where we have the same base on both sides. So again, the main idea here was I had this exponential equation in distinct bases, and all I had to do was take the same log on both sides. In this case, I chose natural log, and that allowed me to use the power rule, which pulls these exponents out. To remind you, the power rule, we have it right here. This is log base a of u to the c is log base a of u, but times c. We've sort of pulled this exponent out. I always think of this as kind of like the pulling pin for if you've ever gone skydiving. A closing pin, sorry. So this is potentially an ugly expression, but from here on down is just algebra. This is just basic arithmetic and algebra. So the big point here is for you to recognize you need to take the log of both sides when the bases don't match. Now, here's a bonus tip. If the bases do match, you can still take the log of both sides. So if we were in the case like, oh, this was several pages back. If we were in the case like this, where I had the same base on both sides, I could potentially just take log base 3 of both sides, and log base 3 of 3 to the 2x minus 3 equals log base 3 of 3 to the 3 times x plus 1. That's last thing, there's a parenthesis. Then I'll have these things cancel out, and I'll get 2x minus 3 equals 3 times the quantity x plus 1, which is exactly what we ended up with here, just with a few more steps, right? So this is definitely a workable solution, but we're just, you know, at this stage we didn't know that we could take logarithms base 3, or many of us probably didn't. So if you see one of these exponential equations, then taking a logarithm is probably a safe bet, although there might be another way that doesn't involve quite so many nasty symbols. Okay, last thing I want to do for this section, one more example, and this is solve for x. And we have e to the 2x minus 1 is positive. Now you'll recall, again, a few pages back, where we did this question of finding the zeros of an exponential. So where is finding the zeros of an exponential? Seem to have lost it. There's e. Finding zeros of an exponential. No. Oh, here we are. Find the zeros of an exponential. Yeah, find the zeros of this function. And the key to observe was that e to the x never went to 0, right? Well, that's going to be pretty important here, but not quite the same. So in this case, I'm going to write this as a difference of squares. E to the 2x is e to the x squared, and 1 is, of course, 1 squared. So I can write this e to the 2x minus 1 positive. This is the same as e to the x minus 1 times e to the x plus 1 positive. Okay? So I've factored this, and I'm treating kind of e to the x as my variable. Now what you can do here is you can sort out when this thing hits 0. And so just like we've done previously, so this is 0, the left-hand side is 0 when e to the x equals plus or minus 1. Okay, well, e to the x equals plus or minus 1, this is the same as when the natural log of, to write this as a logarithmic expression of an exponential equation, this happens when x equals the natural log of plus or minus 1. But there's no such thing as the natural log of minus 1, at least in the real numbers. So natural log of minus 1 makes no sense here, because we're sticking to the reals, which means we have that x changes, the 0 for this thing happens when x equals the natural log of 1, and of course, what is the natural log of 1? Well, that's 0. Okay, fine. So this thing happens when, this thing changes sign when x is 0. So now we just need to check when is this positive, when is this negative. We can do this with a sign chart, by setting up these factors, or in this case, because there's only one place where it can change sign, we've got it changing sign here at 0. So which side's positive, which side's negative. This, I think, is a little easier with test points. If I plug in a number less than 1, so e to the, if I plug in a negative number, e to the minus 2, e to the 2 times a negative 1, that's going to be less than 1, and that means e to the 2 times negative 1 minus 1 is less than 0. So this is going to be negative over here. What if I plug in e to the 2 times 1? Well, that's going to be e squared. I don't know exactly what that is, but I know e is bigger than 1, so e squared is bigger than 1, which means e to the 2 times 1 minus 1 is positive. So we know it's going to be positive on this side. It only changes signs here. Therefore, our final answer is x is positive, or we could say 0 up to infinity. Final answer. Okay, I hope that made some sense, and we'll see you in the next section, which is about the same type questions except for logarithms.